Okay, last week someone asked me a question. How come there is how come there is a half here? All right. It really doesn't matter because later on the next step is DJ, is differentiation. You see, it's differentiation. So when you have a half here, because there's a square here, so when you differentiate, you put the 2 in front, then 2 and 2 cancel, then you get a 1, just to make the maths a little bit not so complicated. Because after differentiation, whatever it is, you equate to 0. So it doesn't matter. If you don't believe, you put a 1 over 100 here, you you will still get exactly the same results. Okay, that is you just go and take a look, you will realize that now. Okay, then I ended the lecture at the Kalman filter here. Okay, just to remind you, this is the most famous filter. All right, Kalman filter. So if you do control, you better don't say you don't know Kalman filter, because then people will think don't know what you're doing. You're really not in this area. At least advanced control, not those very basic one. Now this is the Kalman filter. So obviously it is iterative. We typically start from k equal to 0. So when k equal to 0, the first line you go and calculate kf 0. Now you need some initial condition, that is this p 0 minus 1. When you start, your k is 0, so this is p 0 slash minus 1. All right, typically we give it a large number. So in practice, we simply choose it as the multiply by a large number, which means the identity matrix multiplied by a large number. So typically for my project and so on and so forth, you can choose I times 10 to the power of, or just put 10,000. That is big enough. All right, in practice, people is a large number, so 10,000 is big enough for all practical purpose. So you start. Then you are able to calculate KF. All right. Later on, I will give you the interpretation of this. Choosing this as a large number infinity means you know nothing about the estimate. It basically means that, okay, because this is the covariance of the estimate. So if you put it as infinity, means that I got no sense, I don't know, everything also don't know. So that's infinity. If you put 0, means I know precisely what is the estimate. All right, so that's why if you don't know anything, you put as infinity. Later on, you will see. Just tell you first. Then, so after calculating this, you calculate this. Then you calculate the next line. The next line, again, you have to choose something to start, and it is this one. So you need to know what is the estimate at k equal to 0 based on -1, which means basically, in layman's term, your initial estimate. If you know something, just put. If you don't know, again, just put 0. All right, so this one, when we start, we typically put I times 10 to the power of 5. This one, you don't know, you just put 0. So if you are measuring temperature, then you know the estimate of my temperature is 36, you just put 36 first. You could be having fever, 37, 38, 39, but 36 is a good starting point. But if you don't know anything, don't know, you're not measuring temperature, you're measuring position, you don't know where it's at home or in NUS or what, then you just put 0 there. All right, then after that, you go on this and this, then K equal to 1, you come back the first round. I think that is obvious. Now, then the next thing that is less obvious would be you go and take a look. 52, 53, 56, and 57 actually is what we call, you can pre-compute, which means you can don't go to the lab, don't take measurement, you can stay at home and do the calculation. You see, 52, you just you start as this as I times 10 to the power of 5. And then if you know the plant model, which means C and the noise R2, then you just calculate. You don't need your temperature measurement. You don't need to go to the lab and measure the temperature or the pressure or the speed, or you don't measure anything. You don't need to measure anything. So you just stay at home and calculate this. And after that, you calculate this. Also, you don't need to measure anything. Then this one you have to measure, so you cannot stay at home. This one you got to measure. Why is a measurement? So you have to go to the lab and measure. Let's say the wafer, you need to measure the wafer of the temperature. You have to go to the lab. P, no measurement here. So you calculate at home. This one, calculate at home. You find that you can actually stay at home before you come to the lab, calculate this equation, this equation, this equation, this equation. So basically to get K0, KF0, K0, P00, P10, then K1, KF1, K1, then P11, P10, then K2, and so on and so forth. You can calculate at home. Then next day you come to the lab, then you measure what is Y0, then you go and take K0 from your computer, then you compute this. You take Y0, then you compute this. You take K that you calculated at home, then you compute this. All right. So which means you can actually come to the lab and iterate between these two, because your KF and your K already from KF 0, 1, 2, 3, 4, 5, 6, you all know already. Yesterday you did your homework. So the advantage of this is that if you want speed, all right, you don't have to waste time because computation is fast. No, takes computation time. All right, in case you want to do speed, you calculate this at home first. So when you do the real-time experiment, you don't need computational time to calculate this. You just make use of the one that you have calculated at home. The next statement that I want to make, you also will find that now later on you will see, but I just tell you now, there is such a thing as steady state Kalman filter, which means you iterate K equal to 0, 1 round, K equal to 2, 1 round, K equal to 3. You'll find that, possibly after K equal to 10, you calculate K equal to 11, you find that KF and K and P and PK plus 1 is the same as the previous iteration. So which means it has reached a steady state. All right, you will find that. If then you reach a steady state, then don't need to iterate anymore. Let's say at steady state, KF is equals to 9.5. And that's it. Forever you see KF, you put 9.5. So there's such a thing as transient and a steady state. You will see that you will reach that. All right. So all this you will discover later on when you actually do the computation in the examples and tutorial questions. Okay. So all those things that I say, this can be calculated offline, All right. So let's just put some numbers into the equation so that at least you know how to do the calculation. All right. So the first example would be to do the calculations. So the example is you got measurement. Y0 is 0, Y1 is 1, Y2 is 2. So you got 0, 1, 2. Then you fill in the rest. All right. Of course, the process model, or I give you easy one. This is 1, this is 1, you know. And then R1 is 1, R2 is 1, which means the covariance of this is 1, the covariance of this noise is also 1. So everything is 1, so it's easy. Then, like I say, if you don't know anything, choose this as infinity and this as 0. Okay, so we start. So basically, essentially, it's just put numbers into the formulas that we have. So you go and look at 52, 53, 54, 55, 56, 57. Then you calculate all these da. Basically, 52, 53, 54, 55, 56. So you basically force you to go 1 round, 2 round, 3 round. All right, so let's see. The first round when k equal to 0. So the first thing you do, kf. You see, this is 1, c is 1, this is 1, and this one I say is 10,000. So if this is 1, this is 10,000, you must well forget 1. So it's 10,000 over 10,000, or 10,000 over 10,000 and 1 plus 1. So basically kf will be 1. So that's why you will get kf 1. All right, it's not really 10,000. In practice, this will be infinity. Then, you know, it's or 1 million, you know, 1 billion, whatever you like. So it's 1 billion over 1 billion plus 1. So your calculator, you punch, even you don't know, 10,000. If it's 10,000 over 10,001, you punch into your calculator, you also will get 1. All right, or 0.9999999, that kind. So you get 1. Likewise, k, you will get 1. If this is 1, this is 10,000, this is 10,000, you punch calculator, k will be 1. So that's done, 1. Then the next one, x at 0, 0, which is this one. All right, we say we started off this at 0. This measurement is 0. So this is 0, this is 1. So everything is 0, so this is 0. So this is 0. This one will be this one, k equal to 0, this is k plus 1, so it's 1, 0. So this we say started off, initial condition, we put at 0. There's one part I didn't explain, I forgot, let's say. You see where I derive for you, okay? When I derive for you, I did not include VUK. You could re-derive everything and include VUK. You will find that there's no change. It just appear here. It just makes things more complicated. You got to trace the thing. That's all. All right. Other than that, you just, when I derive for you, my equation, I want to simplify, I didn't put this. So if you put this and do the same algebra, I should be here. All right, and do the same algebra, then you see that this just appear here and nowhere else. Okay, so it's very easy. You trace, you get back there. So now, where are we? Oh, okay, so we are here. Then P00. So P00. So you go and see your P00, which is this one. So you just, all right, this, you go and do the algebra, simplify properly, you will then, is algebra, you will get this. All right, then again, this infinity, the rest are all 1, so this is basically this divided by this is 1. All right, then P10, now this is a little bit tricky. You will have to Also do the algebra. P10, you go to here. P10 will be this one. So let me see. The first thing you do is, you write, so this one I call it P10. Now, is equals to, now the point is, you get A, P, A transpose minus, the point is you must take this from here and substitute inside here and here. All right, if you do that, then the rest is exactly the same. You just let P equals to infinity. You will then find that P10 is equals to R1 plus R2. All right. You don't say that this is 1 and this is 1. It's because numerical problem. This is not exactly 1 because it is this over this plus R1. All right. It's practically 1, but you will get numerical problem. So you want to be precise. You take this whole thing, substitute inside here and substitute inside here. Then when you do the algebra, it will give you this one. Okay? Nothing complicated algebra. You just put it inside. Then after that, you don't treat it as matrices. If you worry, you just treat it as scalar. Anyway, this question are all scalar. Then you just divide out, you will find that it is R1 plus R2. So this is 2. So K equal to 0, we got this. So you just fill in the blanks here. All right, K equal to 0, all the results are here. So then K equal to 1, I think I will not go through because also is going to the same set of numbers and you stick in the number, you go one round, you will get all your values here. So you can look at the values. There's nothing there. Then after that, you look at the value. So make sure you go through one round. At least you must go through 3 rounds. K equal to 0, K equal to 1, K equal to 2, and make sure you get all these numbers. Then you know, okay, I know how to, at least you can tell yourself, I know how to use this number, this Kalman filter to compute numbers, the numbers, okay? All right. So at least you have achieved that. You will get the correct number presented in this table. All right, then, now the next thing I want to say is, be careful, when I teach Kalman filter, the real test is understanding the interpretation of Kalman filter, which will come. All right, the real test is not the maths. The maths is just secondary school maths, substitute here, substitute there, differentiate here equals to 0. All right, find the J, find the minimum, is all that. So the real test, the real understanding for you is not the maths. The maths are not interesting. It is the interpretation. So when you follow my lecture, pay attention to the interpretation. All right, the maths you need to know, but it is not the difficult part. You will be able to figure out because it's basically secondary school maths. Though it's very messy, that's all. All right, part B. Use batch least square to find the estimate at K equals to 1. So now you see equation 16. You see that was where we first started. That was actually how we started Kalman filter. All right, it all started like that. What did we do? We say that, oh, it's a simultaneous equation. All right, there are so many equation, but here at that time, right now, 7 equation, only 4 unknowns. Okay, so how to solve? We cannot solve because none of them will be equal. Only if four unknowns, the first 4 equation can be equal, then the next 3 equation will not be equal. So we'll try to solve as best as we can by writing the least square, by squaring all of them and make j as small as possible, so that each of these equation here basically is as small as possible, at least sum together as small as possible. So when we did that for 4 equations. No, 4 unknown. So you differentiate with respect to the 4 unknown, x0, x1, x2, x3. Then equate to 0. Now you see the point is, at first you got 7 equation. Here are 7 equation, 4 unknown. After doing this, you become 4 equation and 4 unknowns. So we know 4 equation, 4 unknown can solve. Primary school already, you know how to solve. All right. So, and then here we reorganize and write into this matrix. So now go back to this tutorial question. They say solve x11, which means solve for x hat 1 in this, which means solve for this. All right, which means only 2 unknowns. So this was a more general one, 4 unknowns. So you take 2 unknowns, so you basically take 2 rows. The first row and the last row. All right, if you want, you go through this differentiation, you will also end up the first row and the last row only. So if you do the first row and the last row, then x0 and x1. All right, we just apply what we have learned, what we have done for 4 equations. If you want, you rederive using 2 equations. The first one, x dj x0 and dj x1, you will basically get the first row and the last row. If you do that, you will get here. Then the question gave you all 1, so very simple. So this is 2, this is -1, this is -1. All right, all these are 1, 1, 1, so add up together, this is 2. So this is here, and this is 1, so it disappear. The question say measurement y at 0 is 0, y at 1 is 1. So you like that. Then finally, you just find this, you put this over, you invert, then you get this. So now, the real thing comes now. So this is this. Good. And this is also what we calculate 2/3. You look at when we calculate the Kalman filter, x11, which is this one, 1 is here, is 2/3. So I say first, I say again, the Kalman filter actually comes from the least square. We started least square, then we derive the iterative version of the least square. So they must give the same result, and clear enough, it gives the same result because it's just different way of solving the same problem. It started as a least square problem. Okay, now Kalman filter, so that is correct, this and that matches. Kalman filter likes to, in the Kalman filter literature, we will say that this is the estimate of x at k equal to 1 using y1. Okay, so this was least square. When we did that, that was fine. Everything is fine. Then now, the least square give x0 as 1/3. We managed to match this as 2/3. When k equal to 0, the common filter give 1/3. When k equals to 0, common filter gives 0. Least square give 1/3. So now this is the interpretation here. How come this one, for k equal to 1, this is the same as this, but for k equal to 0, this is not the same as this? I seems to say that common filter and least square solve the same equation, but using different roots. All right, how come they are different? So this is the interpretation. Better be careful. When common filter, okay, you see, in common filter literature, this 1/3 would be, how should I write? Is estimate of x at k equals to 0. Now, slash, what is this number here? Okay, be careful. The number here should be 1. Why? Because this, when we calculated this, we make use of y1. Here also make use of y1. All right. Now I say, hey, this one is the same, but this one is not the same. This one, when common filter calculated this number, this was called this is called k0. So this is called x hat 0 slash is kk and k is 0, 0. Common filter calculated this using y0. Calculated the x hat at the 0 sample using y0 only. It didn't make use of y1. All right. So that's why this estimate and this estimate are different estimate. The common filter terminology say this is calculated at sample 0 using y0 up to y0. This one, you notice, is x hat at sample 0. We make use of up to y1. That's why this number and this number, the estimate is different. So to speak, the quality of the estimate also different. This one, we have more information because we have two measurements here, y0 and y1. So this 1/3 is obtained after using two measurements, y0 and y1. This one, the quality of the estimate, so to speak, would be lower because we only make use of y0. We didn't make use of y1. If you have less data, less information to do your estimate, all right, your estimate quality would be not as good as if you have more information before you make a decision or a judgment or estimate. Okay, so that part is the interpretation. So be careful of this. All right, in the exam, don't anyhow give just you all know how the maths is easy. All the formula given, wow, or anyhow substitute, then get an answer. All right, you don't understand them, you will give the wrong answer because there are equations all over the place that can be used to solve. Then you don't know which equation you should solve, then you solve the wrong one. Okay. Now use batch least square to find x hat 2, 2. So which means at the second sample using y0, y1, y2. Okay, so if you go back to here, this is for 4 equations. So you use the first row, the second row, and the last row. So if you do that, you get, then you write things out, you will get here. Okay. Then if you stick in all the numbers, you will get this. Then after that, you inverse, you stick in all the 0, 1, 2, you will get here. Then you get this. So again, I just make sure you know, first of all, this is okay because this is at the second sample. So it's x hat at the second sample. What should this number be? Oh, we use up to y2, so it should be 2, 2. So x hat 2, 2, you go and look at the table, is 1.5. So x hat 2, 2, 1.5 is fine. So this is x hat 2, 2. Then after that, you will find that at the first sample, this is 1. At the first sample, 8, this is 2/3. It doesn't match anymore. How come it doesn't match? I already tell the story already, because if you write properly, this is an estimate at the first sample, making use of y up to 2. So it should be this. This one should be this at the 0 sample, making use of y up to 2 to get this number. So this is half and this is 1. This guy here is 0 and 2/3. Okay, this one is x hat 1, 1, 2, 2, 0, 0. So there are different estimates. All right, be careful of all these things. Now, next is find the expectation. Find the expectation. All right, don't worry about this word expectation. As far as I'm concerned, is find the average. All right, simple words. Find the mean, find the expectation. All mean the same thing. Just find the average. Find the variance. Okay, I gave you a simple example already. What is variance? Variance in simple words is if I gave you an example, find it. Then variance. First of all, if you got 3 number, first of all, find the average of the 3 number. So in this case, it's 0. Then take that number and minus the average and square it, square it, sum it, then divide by the number. So in this case, you have 3 numbers, so divide by 3. This will be the average of the 3 number. So obviously, if you have 1 million number, then you find the average of the 1 million number. So let's say it's 0. Then you will have 1 million square because you have 1 million number. Then below divide by 1 million. That will be your average. No, variance. Then nothing, standard deviation is square root of variance. Okay. So now find the variance of the estimation error. Now, this is important. Estimation error means what? We say that this is the true state. All right, in the terminology, we say that this is a true state. And this is your estimate. So the example I gave is, this is the temperature. You use thermometer, stick into your mouth and measure. This is which is, we say it's the true temperature inside your body, really. But this one is the one that you use the temperature gun and point at your forehead sensor. All right. So then the difference is called estimation error. All right. So this is the terminology. Of course, it is important. If you use the gun, you want to know how far away you are from the true temperature that is inside your body. Now, how come got such thing as estimation error x1 minus x1 hat x hat 1 1? It means like that. So it means something like that. Let's say you go and do an experiment. Okay, every night at midnight, then at 1 o'clock, at 2 o'clock, you go and find the following. You go and do the following. X K minus X K K. So this is K. You go and use a thermometer, stick inside your mouth, measure. Then you use the gun, point at your forehead, measure. So you see what is the difference. So at midnight, you got this value here. At 1 o'clock, you also do the same thing. Then you got this value here. At 2 o'clock, you do the same thing, you got this value here. Then next night, you go and do the same thing. Tomorrow midnight, you go and measure. So you got this value here. This value. Then tomorrow night is Saturday night, go and do it. Then 2 o'clock, you do this. Sunday night, you also go and do. Then 1 o'clock, Sunday night, you go and do. Sunday night, 2 o'clock, you go and do. Then Monday night, midnight, you go and do. Then Monday night, 1 o'clock, 1 a.m., you go and do. Then 2 a.m., you also go and do. So if you do, keep on do, you will have many. I don't know you do how many nights, but if you do 1 month, 30 days, then you have 30 reading. All right, if you do 10,000 nights, then you get 10,000 readings. So now this question is to ask you, at 1 o'clock, what is the expectation, which means what is the mean? All right, so if there are 1,000 of them reading here, you take this 1,000, divide by 1,000, that would give you the expectation of this at 1 o'clock. Understand? All right. So now, the next thing would be, oh, I didn't do it properly. Because it is this, sometimes what you estimate would be less than this, sometimes would be more than this. So this could be a positive and a negative. So I should put some crosses here. Okay, sometimes your sensor say is higher than your thermometer. Sometimes your gun is less than your thermometer, so you have plus and minus. So then you find the average of this. Expectation, then you will have to do the following. Variance, you will have to do the following. Take all this. So we are interested in only at 1 o'clock. Square all of them. So at 1 o'clock, I redraw again. since we are only interested at 1 o'clock. Because we square all this number, so you will don't have minus number anymore, all become plus. So this would be the square of xk minus kk square. So you take this, all these number, you square them. So you square them, you will get positive numbers only. All right. Then after that, the variance would be two step. What? You square them. Then after that, you find the average of this, the expectation of this. That would give you the variance. Okay. So now understanding all this, we'll then do the algebra. So now 52, 53, 54, 55, 57. Let me go to okay, why don't you go for a break, come back then with 52, 53, 54, 55, 56. All right, go, drink some water, go toilet. Okay, so now we want to find x1 minus x hat 1, 1. So let's find x hat 1, 1. Then we find x1. Then we do the subtraction. Okay, then we find the expectation, which is the mean. And then we find the expectation of the square, which is the variance. Okay, this is the steps. So the detail would be like that. Again, you go to what? 52, 53, 54. So let's go 52. You will get KF. So you sub the value here. You 53, you get KK. So you sub the value here. You will get A over C. Nothing to discuss. You just plug it inside. Then X hat 1, 0. So you go and look at the Kalman filter. 1, 0. So which means K is 0. So this is X hat 1, 0. So you sub things inside here. You will then get this. Okay. Then after that, X hat 1, 1. So you go to the Kalman filter, which is 54. So you sub inside here. You will get X1, 1. All right. So with this, you will find X hat 1, 1. There's no point for me to substitute here, substitute there in class. You have to go back and take a look. This nothing more than that. Find x1. So x1, you use equation 58, which is this one. All right. So k equal to 0. This will be give you x1 equals to ax0 plus w0. So ax0 plus w0 is x1. All right. Then you use equation 59. You will replace this with this. All right. And so that's it. This would be x1. Then after that, you take this and this. You subtract each other, you will get this. Okay. Then after that, you reorganize things a little bit. Means what? All right. I just help you a bit. This term stays here. This term also stays here, so it's easy. Now, this is replaced by this. No, it's replaced by this. And then this is replaced by this. Okay, all this, for example, this one is 59. Cx0 plus V0 is actually equals to Y0. All right, Cx0 plus V0 is Y0. Okay, you go and look. Then this one will help you to replace this. Okay, so after that, then there's nothing. You just clean up the algebra, you will get this. Then clean up some more, you will get this. Then after that, this is where the interpretation is. The expectation of the estimation error is 0. Why? Because when we take expectation now of this, the expectation of this is a zero mean independent Gaussian variable. So if you take the expectation of a zero mean, it will give you 0. All right, this is a noise with 0 mean. So this is a number multiplied by something that has a 0 mean. So you take the expectation of it, it will still be 0. All right, so it's like this is a 0 mean. So I give you pictorially, like that, like that, like that. So you look, A is 0 mean. Then multiply by some number, maybe make it bigger. So proportionally, it's just bigger, but it's still around 0. All right, so 0 mean this is still 0. Same argument for this. This is 0 mean multiplied by some number, still give you 0. This is 0 mean multiplied by some number, still will give you 0. Finish. So that's why expectation of these three numbers here, this number here and this number here will give you 0. So expectation of this is called estimation error. Is equals to 0. Okay, then the next thing is, this is variance. Because you square the thing, you notice this square the thing, expectation means the average. So you square first, then find the average. So since it's this, so you square. Now, you square means basically you take this and then multiply by itself, same square bracket. All right, you have WO multiplied by something. Then you have V0 multiplied by something. Then you have V1 multiplied by something. Okay, so you know from maths, you will have to multiply these two square brackets together. Now, the easy part is this W0 will have to multiply by W0 part. All right, but W0 will also have to multiply by the V0 part, and W0 have to multiply by the V1 part. Now, the point is, if W0 is 0 mean independent, all right? And V naught is also zero, mean independent. Means that this W0 and V0 has nothing to do with one another. And both of them are zero mean. So you multiply this with this, you will get still zero mean. All right. So in other words, all those cross multiplication terms, when you find the average, will still be zero. All right. Now left with those that multiply by itself. W0 will multiply by W0 term. That will give you a square, W0 square. The V naught will multiply by the V naught term. That will give you a V naught square. The V1 will multiply by a V1 and give you a V1 square. Now, when you have a square, you know squares are all positive. When you find the average of all positive number, it won't give you zero. It will give you a positive number. All right. So that is the point here. The W0 square, when you multiply this, you will get, how should I put it? W0 square, which is this one here. All right, CF1 minus 1 is this one, is inside here. This one, you take the expectation of this, is by the definition R1. This is the variance of the Gaussian independent variable of this noise at W at sample 0. In other words, I show you the picture again. I say, oh, at 1 that time, oh, if you have all this, then you need to square it. So all these become like that. So that's the first step to find variance, square it. Then the second step, find the average of this. Then you are finding, then it's obviously it cannot be 0. It will not be 0. All this will be 0, but once you square, it will not be 0. So when I find the mean of this, I'm finding the variance of this at k equals to 1. All right, so now I'm finding the variance of W at k equal to 0. And it's given that W, the noise whether the noise that you have, let's say of your sensor, if you use the same, temperature gun, whether you measure at midnight or 1 o'clock or 2 o'clock, your noise is the same noise. The variance will be the same. So in this case, W is R1, V is R2. So likewise, this one, you will get V naught, all right, square, and then the bracket here, which is the bracket here. You have to square it, and then if you take the mean of this square, then by definition, this one gives you R1, this one gives you R2. All right, then likewise, you square this one is the same as this. All right, you get a V1 square, then you get whatever, it is this one. All right, square, then you take the expectation. This expectation, they give you R2 also. Because you use the same sensor, whether you measure at midnight or 1 o'clock, it is still the same noise, R2. Variance of the noise, same. All right, so this would be the variance of your estimation error at 1 o'clock. Okay, question 3. Oh no, example 3. So example 3 says, okay, again, this is your process model. This X would be, let's say, again, your temperature inside your body. This Y is the temperature that you measure using your temperature gun. Then also very easy. C is 1, so this is 1. All right, A. I tell you measurement at midnight, 1 o'clock, 2 o'clock. Then R1 is 1. R2 is 0. All right, find the batch least square of this one, this one, this one, which means your estimate X0, X1, X2. So again, you go to equation 16. Since it's batch least square, we have already done that. And then remember again, why I keep on referring to batch least square when I teach Kalman filter, because that was the starting point. Kalman filter just iteratively solve the batch least square. 16. Okay, 16, we got for 4 unknowns. So now this simplifies to 3 unknown. So you can see I only need to take the first row, the second row, and the last row. If I do that, I will get here. Okay, then since R2 is 0, so first of all, I take this, I invert this, so I get X0, X1, X2 here, so I got this. Then since R2 is 0, so every time I see a R2, I put a 0, 0, 0. All right, you'll find that you get the maths is like that, which means the question say R1 is 1, R2 is 0. So every time I see R1, I put a 1, R2, I put a 0. You go and do, you find that, this one end up as this one. Then it's obvious to see, the estimate at midnight is the measurement at midnight. The estimate at 1 o'clock is the measurement at 1 o'clock, because this is a diagonal matrix. The measurement at 2 o'clock, the estimate at 2 o'clock is the measurement at 2 o'clock. How come? Oh, because R2 equals to 0 means that there's no measurement noise, which means this is interpretation. You see, your thermometer got noise, which means this one, R1, is given as 1, which means the one that you use a lousy thermometer is stick inside your mouth, got noise, is cheap thermometer. Maybe you go and buy a $10,000 gun, practically no noise, perfect one. So you put R2 equals to 0 in your calculation, because you know you got a $10,000 temperature gun, whereas inside there you got a 50-cent thermometer. So which one you believe? Of course, people ask you for your estimate, you will take your $10,000 temperature gun and say, okay, my estimate is according to the $10,000 temperature gun. All right, that's what it is giving you the result. In words, we will just say there's no model uncertainty, no measurement noise. In other words, the measurement using a $10,000 gun is perfect, And so obviously, if I ask you to estimate, you will not follow your 50-cent thermometer, even though it's stick inside your mouth. You follow your $10,000 estimation gun. All right, this is what the calculation says. And it makes sense. Then, okay, part B. Again, you go and measure. So given the measurement, midnight you measure, 1 o'clock measure, 2 o'clock measure. This time round, your thermometer you stick inside is a very good thermometer. So R1 is 0. R2 is 1. So your gun is not good one, maybe $100 or $10 gun. But what you put inside your mouth is very good one. So how will it come out? So we substitute R1 0, R2 0 in 62. So 62 is this one. So you put inside here, you will end up as this. Then how to interpret? You will look, if you end up as this, you look, you will see that, okay, let's see. X2 will be this times this, divide by this. X1 would be this row times this, divide by this. Then you will see, the difference between X2 and X1 is actually A times X1 will be equal to X2. Because you want to write it down for you. So X2 is what? X2 hat is so 1 over this, which is this side. Okay? Multiply by A square Y naught plus A cube Y1 plus A 4Y2. All right. Then what is X1? Again, it's the same. Okay, it's the same times this is A Y naught plus A square Y1 plus A cube Y2. You see, X1 and X2 is just a difference of, if A times this, you will get this. So that's why X2 is A times X1. The pattern is very clear. Then the pattern between X1 and X0 is also very clear. Then you look, but this is the process model, which means process model, you see, this is a process model. X2 is equal to A times X1. And this is 0 because say R1 is 0. Okay. So if give you a simple example, if your A is 1, then you will basically say that 1 o'clock estimate is the same as the midnight estimate. 2 o'clock estimate is the same as 1 o'clock estimate. And it's perfect. This is perfect because there's no noise. All right, so you follow the model. This is what it is saying. If A is 1, if your model A is 1, if your model A is 0.9, then you say it's perfect. All right, 2 o'clock is 90% of the, is 0.9 of the temperature at 1 o'clock, is perfect. 1 o'clock is 0.9 of the temperature at midnight. Maybe your body is like that. Every night, perfect, is always like that. Okay, because your R2, you already mathematically say it's no noise. It's a perfect relationship between the temperature at midnight, 1 o'clock, 2 o'clock. That's what you say when you put R1 equals to 0. Easier to think, the model of your temperature A would be 1. So you are basically saying, guaranteed, my temperature at 1 o'clock is the same as midnight. 2 o'clock is the same as 1 o'clock. Don't even need to think twice. So that's what the maths calculation for that, if you mean that you put R1 equals to 0. And then it will say, you see, you will say Don't care about the reading. Don't care about the temperature gun. So this one has nothing to do. So once you know your midnight reading, your 1 o'clock, 2 o'clock reading are all done. You completely ignore your temperature reading, which means your gun, no matter what you measure at 1 o'clock, never use. You say it's the same as 12 o'clock. You measure your temperature using a gun at 2 o'clock. You also ignore. You say, hey, no, it's the same as 1 o'clock temperature. Okay, this is what you have done. Okay, so now that is now just to make a bit more sense for you, if A is 1, then you will find that if A is 1, you go back to this picture here, all are 1. This is 1 plus 1 plus 1 is 1/3, is 1/3. So if all are 1, what is x0? X0 is y0 plus y1 plus y2 divided by 3. Okay? That is the average of the 3 measurements. What is x1 is also, this is 1, 1, 1. So it's y0, y1, y2 add up together, divide by 3. What is x2? Hat is also 1, 1, 1. So it's y0 plus y1 plus y2 divided by 3. So in other words, you can see you're basically doing what we always do in primary school physics, in secondary school physics. Take 3 measurements, divide by, find the average, and say that that is your temperature. Okay, so maybe in secondary school, you need to measure the temperature of some liquid, you just stick in the thermometer, take out y0, and stick in again y1, and stick in again y2. So what is the measurement? You just take the average. That's what we always do. All right, so now you see it makes sense. Okay, part 3. Part 3. Okay, I give you some measurement now. So y0 is 3, y1 is 1, y2 is 0. A is 0.5. You plot the results in part A. So what you need to do now is part A, 0.5. So you go to part A. Where is part A? Okay, 0.5. Part A is this. A no use one. So then this was given y0, y1, y2 is given as 310. So you stick in 310, which then is your x0, x1, x2. So you plot it. So I plot it. 3, 1, 0. All right. So I plot 3, 1, 0. And also notice what is the cross? The cross are the measurement. So the measurement, the circle is part A estimation. We already say already, part A, because your gun is a $10,000 gun, your thermometer is a 50-cent thermometer, so your estimation is equal to your measurement. So since part C, the question say is 310, so your estimation will also be 310. Your measurement is also 310. Okay, so that's part A. Part B, part B, part B, A is 0.5. So you stick in 0.5 here, 0.5, 0.5, 0.5, you stick in here, 310. So you go and calculate, you will get this. So that answer is plotted here. This is part B. All right, this is part B. Here are the squares. So notice now that part A means that part A is R20, part B is R10. So part C is both also got noise lah. Then you cannot follow part A or cannot follow part B. You cannot trust the thermometer, the gun. You trust the gun a little bit, and then you also trust your thermometer that put inside your mouth a little bit. So give you the interpretation. So you don't follow completely the gun or the thermometer. That's why part C, because you go and do the calculation, you will then get this. And then inside here, you can see part C says it's here, it's here, it's here. Because, all right, the mat say, hey, I cannot be here because doesn't mean I trust the gun completely. I also don't trust the thermometer completely. So depend on the ratio between R1 and R2. The mat say that this should be the best guess. All right, this is what I'm trying to show you here. Oh, of course, in practice, now you got two information. One, the thermometer, one is the gun. So depend on the ratio between the noise between the two, then you go and the maths will tell you how much to follow which one. Okay. So this is all right. Example 4 is the last example that I'm going to do for tonight, but this is heavy maths. So you just follow the next 4 pages of heavy maths. Simple, but very untidy. That's all. Okay. So now, again, is a first order process 5859. What is 5859? Is the simple standard one. 5859 here. No. 58. Okay, simple one. 5859. That is the model. All right. Oh, sure. 5859. All right. Show that if P k plus 1 k is actually the estimation error variance between the true state at k plus 1 and the estimated state at k plus 1 using y up to k only, which means you are not using the k plus 1, you are not using the latest one. So this would be the estimation error of this. And then this PKK is the variance of the estimation error of this, which means X true state at K and estimate at K using the temperature, using the measurement up to K. Then the covariance update are given by 44. Okay, let's do. Are given by 44 and 45. All right, so let's show 45 first, which means show the relationship between this and this. This is 45. All right, if this is defined by this and this is defined by this. All right, since this is defined by this, so this, I write it out. Okay. And then this one, you will use the model and replace with this. All right, this one is replaced by this. Okay. Which means you have to go and look at the equation. All right, I already helped you already. 5836 will help you to replace this by this and this by this. Then after that, is a square. So like before you go and multiply things out, you will get this. Okay, so now, like I told you before, the average of this will be 0 because K is a zero mean independent variable. So this is easy. So this is 0. This is also 0 because this is zero mean. Then this is defined as R1 because this is a square of the random variable. This has been defined as this. All right, which is this one here. All right, so just in case you don't see, this is used in here to get this. Then you say, hey, this pk plus 1k equals to a squared pkk plus r1 is 45. Okay, so I have shown equation 45. If this is the covariance of this, and this is this, which is the covariance of this, then indeed 45 is this. So the covariance between these two covariance is related in this equation. So that's 45. So here to now, we have proven equation 1.45. So now we will deal with 1.44, which is more involved. So now we will deal with equation 1.44. So to simplify the writing, the estimation error between the estimate and the true state, I put it x tilde. All right. If that is the case, then you take this 58, 59, and 35. Basically, x tilde can be written like that. If you, I help you to see this three equation will say that this is equal to this. And then this is the rest. You go and look at the equation, you will find that. Okay? No. This plus this is equal to this. Okay, is equal to this. Then the rest is equal to this. Go and see. Okay? Then after that, I mean, just to help you, there's nothing to explain. Just look at equation. Oh, yeah, it's that. Then after that, use 58 to replace x. So then you see x here. You see all are the same. Everything is the same except the x here is now replaced. So this is replaced by this. Okay, go and look at 58, how you replace this with this. The rest of the things are the same. Then after that, nothing, you just tidy things up, you will get this. And then it is 2 cumbersome, so they just call this F. So this is also F. So if you define this as F, then the whole thing looks like that. At least don't have to write so many things. So this equation with this replaced by F, all right, now looks like that. Then now we need to find the variance. So before that, we square as the first step. So you square this, you will get this. All right, then same story. You see, I give you, I explained for you already. Only the first three terms remains. The cross products, the last six terms all become zero when you take expectation. So you can see. So now the first three terms remains because they are squares, squares, squares. Squares are all positive number. You find the mean, it cannot be zero. Okay, this one, this is zero mean, you will be zero when you find the mean. This is zero mean, you'll be zero. This is zero mean, you'll be zero. Zero mean, zero mean, zero mean. Okay, very easy. So, which means if you take expectation, only take the expectation of the first three terms because the expectation of the last six terms are all zero. So, expectation of this is written here. Expectation of this is written here. Expectation of this is written here. So now, this has been defined as this. All right, you see expectation. PKK is expectation of x tilde k. Or PK minus 1, K minus 1 is expectation of x tilde K minus 1, which means this one. Yeah, no, this one. PKK is expectation of x minus x hat KK. All right. Or expectation of x tilde K minus 1 is P K minus 1 K minus 1. X tilde is the estimation error, which is defined here. So that we don't have to write so long. All right. So that is done. Then again, we say before this one, expectation of this is R1. Expectation of V is R2. Okay, then nothing. You go and rewrite it nicely. You will get this. F was defined as this. So you put back F, you will get this. All right. Then you go and write things some more. Write things some more. You will get this. Okay. So, and this is 144. And so now, basically what we have shown is that you use the covariance. First of all, these are covariance. All right, K minus 1 and PKK is defined in the question like that. PKK and PK plus 1K are defined here. All right. And they are related by this. All right. So it means that if you know this, you can find this. If you know this, then you find this. So step by step. All right. Which means if you know this, KK, you get K plus 1K. Then if you know K plus 1K, you get K plus 1, K plus 1. So step by step, your P can iterate, all right, when K goes from 0, 1, 2, 3, because step by step it goes. All right, so this is what the tutorial question try to show you. The last part of tonight would then be, all right, let's say if, as usual, when you first start, you don't know anything, you say that P0 minus 1, which means when K equal to 0 is infinity. Then you look at 43, it will give you this. What is 43? Okay, 43. All right, PKK, it will give you this. So let's see. When this PKK, this is infinity. So the denominator, you can forget about R2. So it's just this divided by this. So it's R2 divided by C squared. You see? R2 divided by C squared because P is infinity. So you can forget about R2. So the P and P cancel. So left with R2 divided by C2. So you got this. So this is P00. Equation 52 give you this. So you go and look at 52, right? This is infinity, so you forget about R2. So C and C cancel, P and P cancel. So this is what you get, 1 over C. 54 give Y naught over C. 54 is this one, is X00. All right, you stick in Y naught and all these are 0, 0. And KF was already found as this. So you will get Y over KF, which is 1 over C. So it's Y over C. All these are zeros. All right, Y over C. So now, okay, ready? You got this. So you stick it inside here. You stick that inside here. All right. And Y, just help you a bit. You go and find the equation. Y is actually given by this. All right. So X00 is Y over C. We put Y over C here and then replace Y by this. You will get this. This and this is the same. So you do the maths, you will get this. So finally, you square this thing. You square this, which is this. We saw that the expectation of this is R2. So over C squared, there you see, oh, this is equals to P00, which is here. Okay, so it shows you that P00 is actually the expectation of the estimation error at K equals to 0. So this one shows you when we first start, P00 will give you the estimation error variance at K equal to 0. Then when you have these two relationship, I told you before, from then you can, with this K00, you can get P10 from P10, then you can get from here, you can get P11, then from P11, you come back here, you get P21, then from P21, you go back here, you get P22 from here. So you continue. All your variance is continued with this set of iteration equation. Okay, the last thing I want to tell you is that so far I make things easy so that we deal with scalar, if not. But in practice, it will be vectors because your state X will not be one state only. If you measure temperature, that is one state. But if you measure car, then you will two state at least. The position of your car and the speed of your car. Sometimes you may even want to position of your car, speed of your car, acceleration of your car. All right, how much? All this depend on your application. So PKK, we always use just this square because it's scalar. But when we deal with vector, then it will be this, the estimation error, this, a square means this times the transpose of this. Scalar, no such thing as transpose, so we just put a square. But if it is a vector, then you take the vector, multiply by the transpose. Okay, likewise this, the vector multiplied by the transpose. So instead of just like that, which you will not know, so I show you what this means. Next, you will have to do there will be tutorial that shows you, but now I can just tell you. So this is the vector of x1, estimation error of x1, estimation error of x2. The transpose of this vector is here. So P is the estimation of this square, right? When you have vector, it's transpose, multiply itself by the transpose. So if you multiply these two, you will get this. Then basically this is a 2 by 2 matrix. Then you take the average of this, average of this, average of this, average of this. That's why we call the P in general, we call the covariance matrix. All right. If it's scalar, then we just call it, oh, that's a variance. But because it is a matrix, so we call it covariant matrix. Okay, I will stop here tonight. I think there's enough for you to go and I see you next week. All right.